Good evening. Hi, everyone. Um, Welcome to the second half of week 4. Today, we're going to be talking about exceptions, which doesn't actually have a massive impact on your assignment, I guess. But has a little bit of an impact, and even more importantly, I think there's just a certain level of this theory being quite critical to understanding C++. We'll see how we go for timing tonight. There's a very real chance that we actually don't need all of our time, so but you know, we can play that by ear, which is super exciting. I hope everyone's good and happy and well. You know, it's not rainy like it was a few days ago, so that's always a plus. So today we are going through exceptions. Now, I know that a handful of people, well, probably most people, have dealt with exceptions directly or indirectly. Most programming languages that aren't, like most commonly used programming languages, imperative languages that aren't C, have some notion of exceptions in them. C is one of the big ones that doesn't. But C++, like Java, like Python, like PHP, JavaScript, C#, Java, they all have, I might have said Java twice, they all have exceptions. So it's a fairly standard language feature. And Firesin says that I made you swap to Edge. I have to say, just using Edge for lectures, it's not a bad browser. I kind of dig it. It seems really quick. So poor Microsoft's probably having to battle all those years of bad association. What we're talking about today is we're talking about exceptions, obviously. Throwing, rethrowing, no except, all the little details of exceptions. But why we're learning about exceptions is that sometimes our programs have to deal with unexpected runtime errors and handle them gracefully. So exceptions are all about runtime, right? Like if you could totally rule out all runtime errors, exceptions would have no purpose. There would be nothing to worry about when the program runs because there would be no anomalies. There would be nothing that goes wrong or unexpected errors. So exceptions are dealing with unexpected errors. Now, if we start with a simple example, and this is a very C-style example whereby we're dealing with errors kind of defensively or through negative ones and stuff. And I'm just going to pull this up here in our lecture code. So there's a simple example we have in the code. What is it? 455. Perfect. And yes, there's just a little bit of Clang formats made this slightly cleaner. But basically here, think of it, it's got a main function. We print out enter a -1 to quit. We then create a vector with 4 zeros in it. We tell the user to enter an index, and then in a for loop here, we define a print index. We don't initialize it. That's fine because we're going to initialize it immediately after. And then we essentially enter the for loop while this condition is true. There's no need for an increment. There's no need for like a third part of the while loop because the act of reading through standard CN will slowly gobble up the buffer until it's gone. So we're essentially saying this is the initializer and then this is the condition to keep going. So standard CN reading from standard CN into a variable print index. We did some of this in my tute today if you want to go watch that. So we're reading from standard CN into a number. And if you do successfully read it in, then standard CN returns something that is truthy, I believe. So we do that every loop, and then after that we check, is the number we read in, i.e. the print index, is that equal to -1? And if it is equal to -1, well, then we do a break. We exit the loop. And if it's not equal to -1, i.e. we successfully read from standard CN, then we print out item the vector at the index. So basically we take the index, we have to cast it to a size type because here we originally made it as just a standard int, and then we simply get that particular index from the array. Okay, so you know, this mostly works. Try and build this. Oops. What in the hell? Oh. Ah. No kit selected. Great. Okay, build 4.5. Not having a good day today. Okay, stop. Alright. Let's try and make this happen. So we're going to see make build. Why is that trying to build everything? Did I do something strange? Sorry, bear with me here while I make mistakes with a slow VLab tonight. Build target, sorry. Okay. Derp. And the target is 455, but it's not appearing. So weird. Let me just close VS Code. Having a bit of a strange moment today. Great. Okay. Build target. I'm sorry, everyone. I'm just trying to figure out what in God's name it's so grumpy about. There we go. Yeah, okay. I remember reading this on the forum. How strange. How strange. Just gonna pause the recording. Alright, well, that pause was worth 10 seconds. Okay, so anyway, that was strange. Reloading the window seemed to deal with that fine. So I got this exception file. I've just built it. When I want to run it, demo 455. Let me get rid of these silly little pop-ups here. Enter -1 to quit. Okay, so I'm going to enter an index. That index might be like 2, and it's 0, 3, it's 0, 0, it's 0, etc. Then I type in -1 and we quit the program. And then here I can just update these, and I probably should have updated these at the start. We can kind of see the behavior that happens here. So I do index 0, index 1, 2, 3, but what happens when I do index 4 is the program crashes, and it crashes because I try to get something from the vector for an index that isn't valid. Now, what's happening here is that the vector is actually throwing an exception. You can see this in what it prints out. It says terminating with uncaught exception of type standard out of range vector. So the vector is crapping its pants. It's getting mad. It's essentially screaming at the top of its lungs that something's gone wrong, and it's waiting for someone to help it out. So this program works fine until we'd have to deal with an unexpected circumstance, i.e. an unexpected input. So again, these are all things that can't be known at compile time. Typically it depends on something to do with the network, the system, the operating system, the input, a lot of inputs. What we can do though in C++ is when some libraries we use throw exceptions, which means that they essentially create an exception object and say, there's an exception here, and they complain about it, we can handle them. So the normal way of handling things in a C-like program is to essentially either crash the program if it's fatal, but that's not a very good behavior, or you have some kind of return value. So if you think about some standard C-style functions, when things go wrong with C-style functions, you just return -1 or you return false or something like this. Often it's done through the return value because C has no other mechanism. C++ does have a mechanism though, which is these exceptions. And what you'll notice is in this first program, it just crashed the program when there was a problem. But if I go to the second one here, this is very much a similar program, slightly different numbers. But what you see here, I can get rid of this resize for now. What you see here is that I am now catching this exception. So essentially, if the vector, when I call the function, throws an exception, makes a complaint, says that something's wrong, what this is telling the compiler to bake into the executable is, if you see something like this thrown, then I want you to execute this body of code. So now when I go and build and compile this one, it says, enter -1 to quit. I enter 0, I get that number, 2, 1, 3, and then if I enter 5, it says index out of bounds. So a way to think about exceptions is, at a conceptual level, they're not too dissimilar from if error, do this, or like if no error. And you'll see that the way we're handling them is we're wrapping them in this try catch block. This block is pretty similar for lots of different languages, sometimes different names, but try says do something, and if there's an error, catch it. So the way that the program flow is it goes through every single line of this try, and if an exception is thrown at any point in the try, then the try jumps immediately to the series of catches, and it checks, was this the thing that was thrown? Was this the problem that happened? And if that was the problem that happened, we do something. And then if this one was the problem that happened, we do something else. And then at the end of it, we keep going. So the way kind of C++ is designed is like other languages, try, catch, and then you gracefully handle it. So the whole point of exceptions is to gracefully handle problems, because it's better than crashing it, or other kinds of things. So that's like a lot of these lectures, I like to start with a very high level example that kind of captures everything we're doing so that you can at least see how it all fits in. But let's actually get back into the basics of what these exceptions even are. So exceptions are for exceptional circumstances. That means when something goes not to plan. And it happens during what we call runtime anomalies. So an anomaly is something out of the ordinary. So normally you have like a standard straightforward flow you expect your program to follow, but what happens during your program is something strange happens. Maybe someone inputted an invalid number, maybe you didn't get to allocate that memory, maybe the file doesn't exist, like in the word ladder assignment. So C++ has this runtime mechanism for exception handling, and what happens is C++ detects a runtime error and it raises an exception, or a particular class throws an exception, raises an exception. Throws and raises are the same thing here. And one of the most fundamental ideas to understanding an exception is that often exceptions are handled by unrelated pieces of code. And what that means is that it's kind of like jumping around, because normally when you're programming with these kinds of sequential imperative languages, everything just follows like a quite straightforward flow. Even if you have loops and branches and other stuff, you can still put your pen on the top of the page and like follow it around, right? Even if it's all wiggly and waggly. But exceptions kind of break that rule, because the way they work is they say, okay, if there's an exception, stop everything you're doing and immediately start going up through the stack frame to find something to handle. So when an exception's thrown in C++, everything stops, and it just keeps going back through all of the functions that it was called, from this function up to this function, all the way back up to your main function, all the way back up, hoping for someone to handle it, looking for someone to catch it and do something graceful with it. In C++, there are a whole bunch of exception objects that can be thrown. So all exceptions in C++ are objects too. Ints are objects, strings are objects. We've spent the last week or so talking about classes and objects. But all exceptions in C++ are objects too. And the most basic type we have for exceptions is the standard exception class. So this is like the broadest exception. So think about this as like the mother of all error messages, the broadest error message. And then we have a series of like inherited types or like subtypes of that. So, with with exception, we have a logic error and a runtime error, and a logic error has like an out of range and an invalid argument and a length error. And these are all inherited off each other. So if I go look this up in CPP reference, out of range, you can see that this particular class here is inherited from logic error, which is inherited from exception. So these are all subtypes of each other. You can go read more about that on those links. In terms of the exception code structure, exceptions treated like L values. We'll talk more about what L values are next week. And then type conversion also sometimes exists, which we will also try and talk about. I think we have some examples. Where do we have our type conversion examples? I'll show you what that means in a sec. But essentially, what this means is that if an exception is thrown that is a non-const exception, it's happy to cast it to a const. And I know you're probably sitting there thinking, all right, this isn't making a ton of sense to me. So I could actually show you something slightly different here, where let's just modify our program for a second. Let's make our own exception really quickly. Okay, so I'm going to say here if print index is less than 0 or print index is greater than 3, because there's 4 elements, or here I could say items dot length greater or equal to, then I want to throw an exception. So I want to do this just before I actually try and read from it. Except the exception I want to throw, I could throw an exception that's in the standard library. So for instance, this out of range exception that we have here, let's throw that one, because that one seems very relevant and it's a standard exception, which is good. So I could say throw standard out of range like this. And I usually would have to give it some kind of they don't have an example there, but sometimes you have to give it like a little message. Sorry. Edge does this thing, I should really figure out how to turn it off, where like it like tabs. How do we do tabs? New tab page. Anyway, if someone knows how to stop it, when I alt tab it changes tabs, which really messes with me. But we want to throw this exception. Now this is defined in standard except. So standard except is a C++ library with all of the standard exceptions in it. So I can just include that, and then we can try and do this now. So if the index is not valid here, and in fact I might use the subscript syntax here because now I'm doing the checks myself. So I'll just do something like this. Let's try and see if this one compiles. Okay. No member name length because it's size, but that wasn't the main problem. The problem here was that it says no matching constructor for initialization of standard out of range. Does anyone know what I'm doing wrong here? I can try and put a message in, out of bounds. Oh, no, sorry, it's not a... Wait. Oh, it's getting angry about the bracket. I see. Okay, so basically a lot of exceptions won't be created without any kind of string or information associated with it. This is no exception, haha, here. And then we're dealing with one last error, which is saying that like comparison of integers of different signs. It's like, I mean, an easy way to get around this is like, we could just try and use a, instead of doing an int here, we could probably just say standard size type. Size type? I think that's okay. I'm not sure if is it size t or size type? I always forget these ones. Now I'm just messing around with too many things. I think it's size t. Uh, oh no, that's right. Sorry, I'm messing this one up. So the reason I was like, why do we have that int there as a -1? So this is part of the reason why kind of your C style approach isn't really good here, because like we have this index which is an int, and we're using -1 because we only want to read in positive integers, right? But so that's why the casting happens. The other way we could get around this here is by potentially saying, okay, well, let's just create some random index that's like 99999, but that's also super ugly. That's like a terrible thing. It's like, you know, if you enter like 5 nines, we'll quit the program for you, but at least this should work for us. Yep, so now if we go and run this one, we enter an index 0, 1, 2, 3, 4. It says index out of bounds. So what's actually happening here is that this is being thrown. Okay? When you throw an exception, so throw an exception, think about the steps here. This is an object. It's a class. All exceptions are classes. This object is being constructed here. Then it is being thrown. When you throw an exception, what the program does is it halts any further execution. So normally this program is going this line to this line to this line, etc. But it completely stops here. It doesn't execute anymore, and then it tries to immediately. It checks to see if it's in a try catch block, and if it is, it checks if any of the catches match, and if it's not in a try catch block, it ends the function and it goes back up a level to the function that called it. And this is the most important part, and if it keeps going up through all of the functions every time, yeah, it's never really true. I don't know why I had that there. Probably back when it was signed. If it was like, yeah, if it goes through all the functions all the way up to the top, and if it gets to the main function and no one catches it, then it calls standard terminate. Okay, so like, that's why in our previous example here, back in this one, the program just totally ended. The reason the program totally ended was because the exception was thrown. It was thrown by the vector at method, but no one caught it. So it was thrown here inside the at function. It came out of that function into our main function, and then we didn't handle it in our main function, so it terminated the program. And it says this here, terminating the program because there was an exception thrown that was uncaught, no one catched it, and this was the type of it. So that is actually extremely self-explanatory. So in this case here, when I throw this exception, it does the same things. It looks to see if it's in a try block. If it is, it goes and checks the catches. And if no one can catch it, it goes back up to the next level. So if I didn't catch it here properly, like let's say I had a catch here that was for like a different type, like a logic error, then the program will still crash. Oops, sorry, wrong program. It'll still crash when I enter 4. Oh, because logic errors are... Oops. See, this is how inheritance works. Logic error is the super type of out of range. I meant to use runtime error, sorry. So I meant to try and catch runtime error, which is a totally different error. So if I do 4, it says it aborted. So the exception was thrown. It was in a try block, so it went through the catches, couldn't find anything. Then it bubbled up to the next level, and then the main function just terminated. After it couldn't find anything in the main function, it just terminated. Now, in reality, often, you know, you're not always putting throws in the same try block. Quite often what's happening is you're wrapping a try around a piece of code that you didn't write, that you think might throw an exception, such as the vectors .at function, which you know might throw an exception. So you put a try around it just to check. Now, you would have seen before I had this code here. So what this code here does is that these 3 dots are essentially a way of saying catch all. So in this case, it's saying if there's an error that's not an out of range error, I want you to catch it. I want you to catch absolutely everything. Okay, absolutely everything. So this essentially prevents it from ever terminating, because it means that if it doesn't succeed normally, or if it throws an out of range error, or an error that's a subtype of out of range, which there is none, sorry, then, oh, sorry, if it throws an out of range, then I will catch it. And I will print this. And then if it throws something else, I will just say something else happened. Now, what other types of things can there be? I left this note in the slides here, which is for resize, which is a standard vector function. And you can see what resize does is it resizes a container to contain count elements. Now, what are the conditions where it would fail? I'm pretty sure if it's above the capacity, which I think is what I'm trying to do here. So we did this previously where if you construct a vector with 4 elements, then the size will be 4. But if you try and resize it to item size plus 10, I think it won't have the capacity for them. So it should throw a different error. 4. Index out of bounds. Oop, 3. Okay. So no, this one's going fine. What's a vector? What's another? I'm trying to think. What's a vector thing that might fail? I guess if we tried to resize it to something absurd. Right, let's try and resize it to this. See if it runs out of memory or something. 3. Oh, no. This one didn't even throw any. Oh, this one did throw an exception? What happened here? So this one actually crashed the program. So this address sanitizer, this happens because of all the CMake stuff we have baked into your program. If you just took this file here and you just tried to compile it directly, right? If you just tried to compile that directly and then run it, you will see that it will fail. A little bit clearer. So, I mean, this one here, I'm sure the message is baked into it quietly. I can't really see it. It looks like the address sanitizer just figured it out for me. But so that's why we like these little CMake things. I'm sure this is running some kind of... It's running the address sanitizer. Yeah, it is in debug mode. Like, that's essentially why, right? So when we're building with VS Code and CMake, it's in debug mode, so it's adding in all these other symbols to it, and the address sanitizer, and probably, I can't remember if it's running Valgrind or not. But you know, that's how the debugger works anyway. But if we run it directly, you see it actually prints out that something else happened. So what happened here was an exception was thrown on this line here. I'm not 100% sure what exception was thrown. Probably tells us. It doesn't tell us. It's probably an out of memory or something like that. Plus. Yeah, so the exception's thrown by the resize function. Because it's in the try block, we try and check if we can catch it. Can we catch it as a out of range error? No. Can we catch it as an anything? Yes. If this was another type of catch, if this catch had a type in it that was not compatible with whatever items.resize is throwing, then it would also like fail to be caught, and then it will bubble up to the next level. So you have to think about exceptions as these series of levels, you know, and when there's a problem, it just like floats up, waiting for someone to deal with it, to look after it. Now, if we go back to the slides here, the slide we kind of got on a tangent on was this one here, where we said that limited type conversions exist for exceptions. Now, we're going to talk about some of these type conversions, but the most basic one is a nonconst to a const. And what we mean by that is that this standard out of range exception, remember all exceptions are just objects of class types, this is actually a non-const exception. I'm pretty sure, I've honestly actually never tried to do this, but I'm pretty sure you could just construct it like this. You could just say auto OOR equals that and then throw OOR. Because in C++, you can basically throw anything. So like here, if I... Oops, sorry. Let's rerun it. Ugh. If I do 4, it says index out of bounds. So this is actually throwing here. So you have to just imagine that this is an object of a class type defined somewhere in the library, and yeah, we're just throwing that object. But what you'll notice here is we're catching the const version of that object. So what actually happens with C++ is that if you throw a non-const version of an exception, it will happily catch a const version of it. It's happy to do this like non-const to const conversion. So you'll see here, if I make this a const now, this will also work, but let's see what happens when I make this one non-const. And I run it. 4, index out of bounds. So this one was still caught, which is super interesting. Oh, there we go. That's because it did the resize. I'm surprised this one's still caught, actually. Maybe the compiler does something here for us that I'm not familiar with. Because this is a const object that shouldn't get caught. Now, I know this should be a const over here. In general, anytime you catch I'm not sure why that's working. But in general, anytime you catch an exception, it should always be a reference to const type. Now, we'll talk about the reference. This is part of the lecture, but we'll talk about that after. But it always should be const. Why? Const is performant. You're not going to edit the exception. Like, why would you edit the exception? That's so strange. So it should always be const. You don't want the exception to be mutable. But the point is, some limited type conversions do happen. There are some inheritance type conversions. We already saw that when we looked at throwing an out of range and trying to catch a logic error. So there is some kind of polymorphism stuff happening here when it comes to the exceptions being caught. And you can also catch multiple exceptions. So you can actually have many catch blocks, as many as you want. I think one really important thing to note, though, is that for any try block, you only ever enter one catch block. So if you have like 4 catches, you can't enter all 4 somehow. You just like enter 1. So once you enter one of them, it'll never check the other exceptions. So if you have something here like this, where you say, okay, I'm going to catch out of bounds, and then I'm going to catch logic error, even though both of these are candidates for the catch, both of these are compatible with the type that's thrown, it would match on the first one, it would successfully catch there, and then it would never look at any of the other catches. So it only looks at the first catch. Is catch everything good in practice? I don't think so. If you really want to catch every possible thing that can happen, you should go and figure out all the possible things that should happen and write them down, I think. Sure, there are some times where you might want to use it, but generally don't use it just because you couldn't be bothered to figure out what might be thrown. Does that make sense? So like, particularly if like, it's like hard to say, like if your function should never throw an exception under any circumstances, should always it should not allow an exception to bubble up to the next level. And your function is calling a series of functions that have some very undefined behavior, then or very just, vague broad behavior, then maybe it's useful as a complete stopgap. But again, it's never there to avoid having to understand what happens. Devansh says, why do you need out of bounds in curly braces? Wouldn't line 18, I might have changed line 18. It's still there, I guess. I'm not too sure what you mean. Why do you need out of bounds in curly braces? Do you mean like here? Oh, so it's like when, I'm pretty sure the constructor of an exception requires some kind of message, some information about it, essentially. So if you try and throw a standard exception, Where is it? Yeah, I don't know. I was trying to look for a random example. But generally speaking, all messages, all exception messages are attached, have some kind of message associated with them, because then there's going to be some context, some circumstance relevant information. So in C++, you can throw any object. I could throw a standard string. I could throw a standard string hello, like this. That's totally doable. I have a feeling that I won't get this to compile though. Oh, no, okay, we're lucky. This works. This does the thing. It's just it calls the something else happen here because it doesn't match this type and it doesn't match that type. Python says, so usually would you do something like standard cout e.message? Yeah, exactly. So that's a great point. That's something I glossed over here. So because every exception has some information attached to it, you can actually print out that information. So here I could say I think it's message. I'm going to take your word on that one. But yeah, so for instance, if an exception's thrown like an out of range and you want to catch it and give the user some information about it, isn't it .what or something? I can't remember. What is it? Standard exception. Let's go grab the one here. Someone will tell me before. .what. Yep. Okay. So it's .what, and .what will give you like the whatever text information was attached to it. So here when I run this one now, and do for, it says out of bounds. You could throw an int and catch an int. That'd be weird, but you can definitely do it. And if I get rid of my silly little custom exception check here, and I just stick to using items.at, and I just get rid of this resize, and we rerun it, now I'm printing out the what from the exception that I'm catching. So items.at might throw an out of range exception, and I'm going to print out the message that it gives me. And now when I run this, for, it says vector. Is that what I wanted? Did I do that wrong? Nope. It just says vector. The explanatory string. Okay. Interesting. I'm sure there's like different ones for different. I'm not sure why they just populate that with vector. Gert says, I guess it's not all too helpful to throw stuff that are not exceptions since you can't assign a message. Yeah, exactly. So exception objects in C++ are literally just classes of a certain type that have a certain standard. So the reason they all inherit standard exception is because then they all have a standard interface. So standard exception implements the, it overloads the equal operator, and it has the what function which returns a string. Yeah, chasta. So that's why everything inherits it, because you could throw other things. You could throw a book, you could throw a point, you could throw a person, but why would you do that? It's really weird. Like, people aren't used to catching these non-exception types. And if you make your own exception, you would typically inherit an exception type. You might inherit standard exception, out of range, you could inherit any, but as long as they're a subtype of exception, you should be good. Firesin says, would you ever not throw an exception? Not that I can think of. I've never come across that scenario. You'd pretty much always throw an exception, and if you don't have an exception that you feel adequately satisfies your situation, make another one, but it should be a subtype of it. So you can see here, here's a bunch of exceptions. The ones on the slide are just some of them, but you can see we've got regex error, format error, bad cast, yeah, whole bunch of things here. Future error. It's a future error. Thrown on failure by the functions in the thread library that deal with asynchronous execution of shared states. Cool. It sounds hard. Anyway, that's the gist of it. So I think that's most of the key things here. This is a great opportunity to explain the difference between .at and the subscript. So we said previously that like .at and Subscript do the same thing. They both like get an element at a given index, but the .at is actually the same logic, but it's wrapped in an exception. So it does the bounds checking with a simple if statement. And if the if statement fails, it throws an exception. And you'll see this here. When I run this and I do normal indexes, it's totally fine. But when I do a different index, well, in this case, the address sanitizer is like, hey, what are you doing? Because it's like heap buffer overflow. It can tell I've done that. But if you are, say, building this on release mode, where it optimizes out all the debug information and all the like sanity checking, and I build this one here, and I'm sure all of you know about release mode from assignment 1, and I run this again, and I go 3, 2, 3, whatever, then I do 4, I am in the undefined behavior territory where things are really scary because this program is still running validly. And this is, again, the worst kind of thing that can happen, is that your program doesn't crash, and we were just accessing a whole bunch of memory that we were allowed to, but wasn't meaningful, until I accessed a piece of memory so big that the actual operating system itself said, no, and then gave me a segfault. So we like exceptions. They do add a bit of performance hit though, right? That's why C doesn't have exceptions, because it is slower. The other thing that's bad about exceptions is it does break the linear flow of the code. And what I mean by that is that here, if I have a standard C out that's like, I love being printed a lot, like that, you'll notice here that if I go and build this one, and I run this one, and I do 1, 2, it's always being printed out, right? But you'll notice when I do a 4 here, as in something that's out of bounds, well, this one will still print it. I forgot to change the other part of the code. So this is undefined behavior. We're accessing an invalid index, but if I change this items index to items.at, that's what I meant to do before, I'm sorry. And I go 1, 2, 3, and then I go 4, you see what happens is that when the exception's thrown here, the program stops on this particular operation. So this operation of trying to get the value at that index, it stopped there. It didn't execute the new line. It didn't execute this line. It stopped everything and went straight. It like stopped that entire try block and it went straight to the catches. And that's one of the most important things. If you aren't already familiar with this from other courses, the most important things to really get your head around when it comes to exceptions are that it's one of the few things in imperative programming that is nonlinear. It's basically go-to statements under the hood, I'm pretty sure. Or if you're a hardware person, it's like interrupts. It's a way of jumping. And that's kind of why if we go back to the notes, we define exceptions as... Where is it? Yes. Exceptions are thrown, they're raised, and then another unrelated part of code captures the exception. So it breaks that kind of linear flow. So people in the chat are talking about Control C. And yeah, I know Control C is not an exception. It's a signal to, it's like an operating system signal to the program that I'd like you to stop, please. Though I believe that, as people have said, some languages like Python will sometimes pick up on that signal and throw an exception, which is interesting because you can actually write code that like might pick up on that signal and handle it like an exception as opposed to just crashing, though I don't have much expertise in that area in the slightest, so I'm not sure. Okay, so we've kind of talked about this a little bit. We've talked about the conceptual structure of exceptions. Now we have the multiple catch options, which we've also talked about. I know these lectures might feel backwards, but I kind of prefer just to show you and then let's explain the key things of it. And I want you to remember again with this that this does not mean that multiple catches happen. One catch happens per try-catch block, right? So multiple catches mean multiple options for a single catch. Potentially no catches, but up to one catch. Now, one of the biggest and most important parts of dealing with exceptions is catching it the right way. Now, we've already talked about when you catch exceptions, you want them to be const. But what we haven't talked about is whether they should be a reference or not. So there are three fundamental ways that you can catch exceptions. They are essentially catch them by value, right? Catch them by pointer. No. And catch them by reference. Okay, so what that means is that in a piece of code like we have here, these are all caught by reference. If I get rid of the reference, it's catched by value. That makes sense? You know, const out of range. C++ will copy the entire exception object in, just like any other object. It'll call the, it'll have a copy constructor that'll copy it in for us. But then it's like catch by pointer. Well, this one's kind of tricky because some exception, you could throw a pointer and catch it. I'm not even going to demonstrate that to you because it's kind of chaos, but nothing is really stopping you from like catching a pointer of something. We would never do that. So we never want to catch by pointer. We never want to catch by value, and we always want to catch by reference. Now, the reason we want to catch by reference should be pretty obvious to you. It's that when you catch things by reference, they are quicker because you're not copying things. What if an exception object has like a message in it that's like 100 bytes? That's like 100 bytes you're copying. You know, that's like a non-negligible amount of bytes. That's some serious cycles for some computers to do. So we always like to catch by reference. The other thing about references, which is really interesting, and we will talk about this I think in week 9, is there's this thing called the slicing problem, where essentially it's to do with polymorphism. And if you catch by value, there's some instances where essentially your type might get cut off early. It's kind of hard to explain, but you could lose data, essentially. If you catch by value, due to how inheritance works, you might actually lose information about the exception. You can click on that link. It's a blog I found, which I thought explained it well, as to why you should always catch by reference. But we always want to catch by reference. But let's actually play that out in reality. Maybe before we do that, because we kind of have just a couple of things here. Maybe let's take an early break. And then we can talk about the rest of catching by reference. We'll probably finish early. So anyway, let's take a 5-minute break and then we'll keep going with this. Cool. Sounds good. So what we're looking at the moment is catching by reference. So we've already talked about const is the right way to catch it, because you can you can promote non-const things to const. And we get the general gist of by reference. You know, it's faster, no random problem that Hayden says we'll learn about later. But let's first have a look, just to really demonstrate it, about what happens if you were to try and catch by value. So this is a bit of a strange little thing, but let's try and follow the flow in this program because it's kind of interesting. So in fact, I feel like this is one of those ones that doesn't... I've had to put some voids in here to make it compile, but we've got this class called giraffe, and when we construct it, it prints giraffe constructed. When we destruct it, it prints giraffe destructed, and when we copy construct it, it prints giraffe copy constructed. Okay, so and it does actually copy constructed. So this is just an example of us printing out to terminal the kind of the key things that are happening. So when you actually look at the flow of this program, we start the program. In a try block, we try and call llama. If llama throws an exception, we're happy to catch giraffe and then print caught in main. So if we catch the giraffe in main, then we print caught in main. When we call llama, though, what happens is we call a function that itself has a try statement called zebra, and we're expecting that this zebra function call might throw an exception, so we're ready to catch a giraffe object. And then we'd print caught in llama, rethrow. So Where's the rethrow thing? Did I delete some slides? Oh. I just got them the wrong way around. So sorry. We'll talk about that in a sec. So essentially here, you'll see that there's this little line of code on line 19 that says throw. So one thing that we didn't really touch on in the earlier example is that you can rethrow an exception after it's been caught. But just to be clear, this doesn't send it along to the next catch statements. This immediately bubbles it out. So if you call a throw within a catch, what it does is it takes the exception that's been caught and it immediately rethrows it up a level in the stack frame, if you will. So what's happening here is if we catch a giraffe inside the llama function, we're saying caught in llama rethrow. So that means if you just write throw by itself, you could write throw something else, right? But like throw by itself will just throw the exception that's been caught. And we call the zebra function, and all the zebra function does is it throws a giraffe object. So on line 11 here, the giraffe object is constructed and thrown. So this is essentially just a function that throws an exception. And then we catch it in llama. So this is because we called zebra here, we catch it here, we print caught in llama rethrowing, we throw it, which immediately sends it out of the function, up a level, to the main, which is where we called llama, and then we catch the giraffe there and we do something with it. So this is an example of us catching exceptions on 2 occasions here. So we've caught it inside llama and we've caught it inside of the main function. Now have a look at this when I try and run it. So if I take this program and I try and build this, we get giraffe constructed, giraffe copy constructed, caught in llama rethrow. Like, I'm not going to be able to show you that, but let's look at this, right? So first thing that happens is we call main and call zebra, call main, which calls llama, which calls zebra. So when we first create the giraffe exception, this exception is constructed here. It gets thrown and then it gets caught here in llama. But because we're catching by value, it's actually copy constructed because it's not being passed by reference. So when that exception over here gets caught inside the catch over here, it has to get copy constructed. So we call the copy constructor, then it gets caught in llama rethrow. So we throw it up again. But before we throw it up, the exception that we created inside the scope of this try catch block has to be destroyed. So we actually have to destroy that giraffe. And then when it gets caught inside the main function, we have to copy construct it again. Say caught in main, destruct it at the end of that try catch, and then the original giraffe gets destructed after that. So it's a lot of messing about. That's the point. Now, the next example, this one here, catch by reference, I won't even show it to you because you can fix it easily. Now watch what happens when we make these all const references. So just the reference would be enough, but we're going to do const references because that's what we want you to do. If I run this one again, and now I run it, you see that we're doing a lot less work. Now you already know this, but I think it's a good demonstration here about object lifetimes, construction, destruction, because you can see it's like giraffe constructed, caught in llama, caught in main, giraffe destructed, which is kind of the flow you'd expect. You'd expect the exception to be created when it's thrown, passed up until it's not used anymore, and then destructed at the end of that. So that is why we like to catch by reference, because if we catch by reference like here, then we're having less memory be wasted essentially. I talked about rethrow already. If for some reason, so sometimes you might want to rethrow an exception. The cases of rethrowing an exception are usually when you want to do something with it, or you want to print something or anything like that, but you also want it to bubble up for someone else to deal with. As in you're like, okay, maybe I want to, one of the best examples of this is a logger. So if you write a logging class for something, you might want to catch an exception, log something about it, and then throw it up. Because your job isn't, you haven't handled it, right? Like if you're just logging it, you haven't solved the problem. You've just taken some information from it. So sometimes it's pretty normal to rethrow exceptions. That can kind of happen sometimes. But the point I was making before is this doesn't send it to other catches. This sends it immediately out a layer. So in this case here, if I have a try catch block like this, and I throw a T and then I catch a T by reference, and then I throw it again, what happens is that original exception that I've caught gets rethrown as if it was never caught to the layer above. And then this try catch here catches it. Now another question that gets asked sometimes is what happens if I don't have my exception in a try catch block? What happens if we call zebra like but outside of the try catch? Because zebra the function simply throws an exception. So let's try this one now. What do you notice about this? Well, what line disappeared? Caught in llama. This makes a lot of sense because what happened is we called it here, it got thrown, but because it wasn't in the try block, it didn't get caught. So only things in the try block are the things that are getting caught. The way I like to think about try is like, when you say try, you're essentially saying, okay, I want you to watch this part of the code because I think this part of the code might throw an exception. And if it does, this is how we're going to catch it. But in this case, because we weren't watching it, this try block had no effect. But it did have an effect here in the main function because we called llama inside the try block. So even though we called llama, llama called zebra, zebra threw something, that thing thrown, it bubbled up to llama and then it bubbled up to main. But because we were watching it in main, we caught it, and then we dealt with it. Whereas if I take this here now, do that, and then I build it again, what happens here? We never caught the exception. Program terminates because exceptions that aren't caught before it hits the top of the program cause a standard terminate. And it says uncaught exception of type giraffe. Yeah. That's rethrow in a heartbeat. Yeah, I guess so. Generally speaking, you probably don't want, I mean, this is just a dumb example that you can play around with if you want to explore the limits of this thing. But doing multiple, like nested try catches are not advisable. In reality, all programs are effectively nested try catch blocks because when you have a try catch that calls a function that has a try catch, they're essentially nested. But you will never have a reason for it in one function to have, I don't think you will. You shouldn't really have a reason for it in a single function to have multiple try catches. Though just for demonstrative purposes, like, you know, this here shows you the kind of behavior about how it bubbles up through the layers. Some horrible things here. You can see we've got, you know, things by reference. Again, this is not like a, oh, you should do this. This is like a, you know, if you really want to poke around with things, you can. But yeah, the actual logic of exceptions is extremely straightforward, particularly if you've already done it before. Now, most of that is fairly known to you. Where we want to get a bit more into the theory on this, there's a couple of things. The first one is exception safety levels. So this is not a specific thing to C++. Other languages have safety levels of exceptions. And the idea is that any exception throwing function will have a certain safety level. And that safety level tells you what guarantees it provides. And there are 4 key safety levels we're talking about. The first one is what you might call a no-throw safety level. Then there's a strong exception safety, weak exception safety, and then after all of that, there is the no exception safety. And these are all decreasing in how safe they are. So no-throw is the safest, and then no exception safety is the least safe. We're going to go through each of these 4 types. So firstly, no-throw guarantee. This is a no-throw exception safety level. It's also known as failure transparency. And what this is that all operations are guaranteed to succeed even in exceptional circumstances. And what this is saying is that exceptions may occur, but they're all handled internally. So, for instance, if you have a, what's an example? Standard vector. In C++, you might have a standard vector, and there might be a function you call such as .empty. Now, .empty does not throw exceptions at all. But what that means is that the .empty never allows an exception that's thrown to come up to you. Now, in reality, .empty probably doesn't even throw an exception, right? But the point is that things like this, it's not so much saying that no exception ever occurs when you call it. What it's saying is that if an exception ever occurs, it will handle all cases and you will never hear about it and you will never know about it. So that's what a no-throw guarantee is. It's saying that it guarantees you that it will not throw something to you. It might do something internally or whatever. And essentially anything with the double dots is a no-throw guarantee. So this example we had here together, if you have a potentially throwing item like this, but you're catching every instance of it, you don't need the ... right? Like items.at only throws one exception. But if you catch it and you never rethrow it, then that essentially becomes a no-throw guarantee. Because something bad might happen, right? Some exceptional circumstance might happen, but you're dealing with it. And that's the crux there. So exceptions may occur, but they're handled internally. Examples of these are freeing memory, anything done in constructors, closing a file. Some of these things might actually have to deal with issues, but you get guarantees that there'll never be an exception thrown. So they're the best kind. The next two are a bit more complicated, which is strong exception safety and weak exception safety. Strong exception safety, if you're familiar with databases, it's very similar to kind of the rollbacks. But strong exception safety says that you call me, I might throw you an exception, right? I might raise an exception. However, I guarantee you that I will make sure nothing is corrupted. I will make sure that if I've modified anything, that I will unmodify it, and I will roll it back. So an example of this, for instance, might be, and again, I'm just speculating on these to something that's somewhat intuitive. But let's say you have a particular, with a vector you have this reserve function that increases the capacity. This one actually mallocs memory, right? It does like a resize for you. It reserves more memory so that future dynamic reallocs aren't as costly. But you can see that this one throws exceptions. It might throw a standard length error if you just ask for too much. It might throw an error from the allocator. So essentially, if it calls malloc and malloc fails, it will, return to you. Like it'll return that exception to you. What a strong exception safety guarantees is that there will be, if it modifies your data structure, as it's modifying it, if it fails, there will be no side effects. Nothing strange that happens. It'll be as if you never called it. Now, this is a good thing that happens, and this happens in databases sometimes. So like in database design, you can kind of do a thing where you say to a database, you're like, delete X, delete Y, and delete Z. And you treat this as a single request. And what happens is if it deletes X and then it deletes Y, but then it fails to delete Z, it'll unwind its changes. It'll make sure that the state you called it in is the state that it finishes with. So it handles that unwinding or rollback internally. So essentially it guarantees no side effects. That one's really useful. This happens for a whole bunch of things like, this should happen for a whole bunch of things like copy constructors, or anything that really mutates it that could potentially fail. Like if your pop back fails, if you do something that mutates your container and it fails halfway through, it should make sure that it's in the same state as when it started. To ensure strong exception safety, we generally follow a fairly straightforward principle, which is that you do all of the operations that may throw, but don't do anything irreversible first. and then you perform all the operations that are irreversible but don't throw. So here you see there's this nice little diagram that's like, if you're writing a function that should have a strong exception safety, so it might throw exceptions but no side effects, then you want to do everything like allocating memory, copying things that are totally reversible. You can just delete the copy, you can just free the memory that you tried to allocate, because these ones might throw, but they're all reversible. And then there's things that aren't reversible that don't throw exceptions, and you do them after, such as freeing memory, closing files and stuff. So when you're trying to write a function that provides a strong exception safety, that's the process you should follow. Then we have weak exception safety or basic exception safety. Did I call it weak before? Oh, it's the same thing. Basic, weak. And this is also sometimes known as a no-leak guarantee. And essentially, this is kind of like a basic version of the strong exception safety, where it says, you know what, there might be side effects. I might have created unnecessary copies. I might have deleted something I shouldn't have. Your data structure might be corrupted. But it guarantees you that there's no resource leaking. Basically, it's like, I will not leak memory. So it's a very poor form of exception safety, but it at least guarantees you that if you call it and it throws in exceptions, it's not going to leak memory. Yes, there's some more detail to that we can keep coming back to. And then the last one is no exception safety. So this is saying that, oh, if you call me and I throw an exception, I might have malloc something and won't clean it up. Or there might be side effects. So you never want to write anything that has no exception safety or no exception guarantees, because that's just bad code. So you would avoid that. But that's definitely a level that you would consider that might exist. I'm sure some of your code might end up like that. A very kind of critical thing you've probably seen around everywhere is this no except specifier. Now, on a lot of function definitions, you might have seen this throughout CPP reference, you might have seen this in the spec or other places. Sometimes you'll see this word no except, and this no except word comes after the function parentheses. It often comes near for class members, it comes near the const qualification. So it's often like return type, function name, parentheses, no except. And this is essentially it's a form of like code documentation that specifies whether a function can throw or not. If you write no except next to a function, then what it is saying is that it has a no throw guarantee. Okay, so there's no chance it's going to throw. If you don't write it, then you're saying there's a chance it's going to throw. What's really important here is that when you write no except, there is nothing about that stops exceptions from being thrown. So if you're defining a function that's no except, that's just a signal to someone. It's not actually stopping a bad thing happening. So why do we do it? It's clearer to programmers. It helps us know what we don't ever have to wrap in a try block. And there's some cases which I'm not super across where I know that I've heard that some STL functions can operate more efficiently on no except functions. So basically, if your program's not having to put code in a try block, then that's less work it has to do, which is potentially more efficient. You can see no except keywords everywhere. Look at this one here, standard vector reserve. There's no except keyword, which means it might throw an exception. But if I go to say size or empty here, size has a no except next to it. Bool has a no except next to it as well. So if you see these around, it's usually that there's no chances an exception thrown. In your assignment, we expect you to put no except on functions that are no throw as well. Speaking of your assignment, one of the last slides that have been added in here is a bit of info about testing exceptions in Catch 2. As part of assignment 2, you will have to handle catching exceptions. Okay? You don't have to do is it catching? No, sorry. As part of assignment 2, you'll have to deal with throwing exceptions, which is the easy part. you won't have to deal with catching it because you're not writing an implementation. You're not writing you're not using a Euclidean vector, you're writing a Euclidean vector. However, you will need to test your code, just like assignment 1. And one of the biggest differences with assignment 1 to 2 is that in assignment 2 you're potentially throwing exceptions in your code. And we expect you to throw them correctly. So for you to tell if you're throwing them correctly, you want to test your exceptions that they're throwing correctly. And there's a few new catch2 functions. These are all just in the docs that you might find really useful. So we have catch no throw, we have catch throws, and catch throws as. And what these functions are is you can essentially like go back to week 1. You can essentially do something like in your section, you could say check no throw, and then call a function like vector.at10, right? So vector.at10 is an expression, and if you give that expression to check no throw, it will pass if it doesn't throw. And then similarly, if you give an expression to check throw, it will pass if it throws. And the other one we see here is check throws at. If you try and check if vec.at10, you can check if this throws, but you can be quite specific about the type. So you could say standard out of range, like that. You give it a type. So there are 3 really easy ways to actually write tests to check if the code you write throws an exception correctly. In this case, I've just used a vector. And you can also use requires. So any of these checks can be replaced with requires if you want. Yeah, and here's these are just some examples. I've just written them in there. Same thing. So checking with catch2 is really easy. Of course, that'll never stop people from being like, oh, I'll just do in my tests, I'll just be like, well, I'll just try this, and if it throws, you'll just try this. And if it throws, like if you catch something, like catch everything, then I will just check false failed. Like some of you might try and do this, right? You might just try and catch it and crash the test, but that's terrible. That'd lose you marks. So you really should be using the built-in catch2 functions in this case. Speaking of that, let's take a really quick look at assignment 2 again. So I said we're not going to read through everything. Firesin says, what about constructors for no except? A lot of constructors would have a not a no except, because constructors are always potential. A lot of constructors are potentially throwing, especially if you're dealing with input that could be invalid. So yeah. But back on assignment 2. So just because we have a tiny bit of time here, and maybe I'll just clone this quickly. Actually, let's chat about assignment 2 for 15-20 minutes. That's pretty much it on exceptions. I don't think I have anything else to add to that. So hopefully that's enough. It's pretty straightforward, and I know most of you have a background in that already. So